Hey all, let's use run expectancy to see how good a base stealer we need to be for stealing bases to be worthwhile. Remember that stealing a base is a base running action in which the runner, during a pitch, right, when the pitcher has the ball, runs to the next base before being tagged out. Right, so you effectively get a free base from this. It's a great thing to do if you can do it, if you're good at it. If not, well, then you're tagged out and you've lost your position for free. So it's good if you can do it, bad if you can't. Runner stolen base percent, denoted SB percent sign, is just the number of stolen bases divided by the number of stolen bases attempts, which is the number of stolen bases. Like, if you want to look this up, it's the number of stolen bases divided by the number of stolen bases plus caught stealing. Okay? That's the formula. Now, of course, there are some obvious cases, right? If a runner can always steal a base, then they should always do it. If a runner can never steal a base, then they should never do it. But there is some question about what is the minimum optimal or the minimum acceptable stolen base percent, right? Because the idea is that on average you want a stolen base to be good, right? But if you're not very good at stealing bases and you're more likely to get out, well then on average you're costing your team runs. So I'm going to guess 50%. Say, whoop. I think, it's probably just as good to steal a base as it is bad to make an out. So a stolen base percentage of 50% seems reasonable. Okay? Now, in order to answer this question, we need to define a term very quickly, the expected value. This is a very, very fundamentally important concept in statistics. We've actually used it when finding the leverage index, right? When we find the plus WPA, the negative WPA, we were using expected values, right? So what we're going to just say is if X has outcomes, we'll just be very simplistic here, X1 and X2, because for our cases there are only two outcomes, you steal the base or you don't, then the expected value of the variable X is X1 times the probability that X equals X1 plus, just to be clear, that's X1 plus X2 times the probability that X equals X2. So what we're going to do is we're going to find the run expectancy gained from successfully stealing a base, the run expectancy lost from getting caught stealing, and compare them. All right? So the expected value of stealing a base, or I should say of a steal attempt, I'll call it a stolen base attempt, equals run expectancy from a steal times the probability of a stolen base plus the run expectancy from getting caught stealing. Maybe I'll say run expectancy from a stolen base, actually. I think that's a bit better. Times the run expectancy from a caught stealing times the probability of getting caught stealing. Right? Those are the only two possibilities, right? Either you steal the base or you get caught stealing. Okay? Well, we don't know about the run expectancy from stealing a base, right? That's what we're going to use. We're going to use the Greg Stoll's website to figure that out. Probability of stealing a base, or just, that's really just That's what we're interested in, so we're going to call that the stolen base percent. Right? We also don't know the run expectancy from getting caught stealing, but the probability of getting caught stealing, if you think about it, is 1 minus your stolen base percent. Okay? So we're going to keep it like that. Let's assume, for simplicity, that we're going to be stealing second base. Suppose there's a runner on first. Suppose there's none out. Just make it nice and simple. Yeah, I know we're simplifying the problem, but we want to make it nice and simple, right? And this person's running to second base, okay? So let's see what we've got here. It turns out, this is not something we would know. We would have to go to Greg Stoll's website here. Let's assume there is a runner on first base. Note that there are 0.87 expected runs. Let's write that down in our notes right here, okay? And we're assuming 0 out, okay? Okay. Now, if you successfully steal second base, well, guess what? You go to second and there's 0 outs. Oh, now there are 1.111 expected runs, okay? So the run expectancy from stealing a base successfully, from stealing second successfully, is 1.11 minus 0.87. Right? Because that's how much we gained. That's how much run expectancy we gained from stealing second as opposed to from just staying on first. All right? Now let's do the same thing except assume, oh, man, we got caught stealing. Now there's no one on base, and now there's 1 out. Well, now our expected runs dip to 0.26. Not so good. So now it looks like it's going to be 0.26 minus 0.87. That's our new run expectancy if we get caught stealing. Or that's sort of the change in our run expectancy if we get caught stealing. Times 1 minus our stolen base percent. Right? Definitely don't want to get caught stealing, right? And just to simplify stuff, 1.111... I think that's 0.24 times our stolen base percent. Minus, right, because this is negative, I think it's minus 0.61 times 1 minus stolen base percentage. Yeah, so man, that's a pretty bad loss if we get caught stealing, right? We lose a lot of run expectancy, okay? So from here, we want the expected value of a stolen base attempt to be greater than 0. So we want 0.24 times the stolen base percentage minus 0.61 times 1 minus the stolen base percentage to be greater than 0. Okay. Well, if we just do a little bit of algebra, this is 0.24 times stolen base percentage minus 0.61 plus 0.61 times stolen base percentage to be greater than 0. See what we did there? We distributed the negative 0.61. Okay. Note the negative becomes a positive when we multiply it by negative stolen base percentage, right? And then I think we can do a little bit of adding together. We get 0.85. 0.85 times your stolen base percent minus 0.61. We want that to be greater than 0. And so that means that our stolen base percentage has to be greater than 0.61 over 0.85, or 61 over 85, which, if we do that on our calculator, that looks like roughly 3/4, so it's roughly 75%, but let's do it out. 61 divided by 85 gives us about 72. About 72%. Okay? So if you want to be a good base stealer, if you want your base stealing to help your team on average, then you need to be able to do it at least 72% of the time. Thanks for watching.